puns are my favorite. This coffee from Monk's Beans growing on me. Pretty good. Okay. I mean, hopefully not. But
really fast, I'll be honest with you. That just went.
I really.
You have to have that coffee, and then you just get used to it. You're like, it's not that bad.
Is that how students experience my classes too?
Yeah, this base is
like,
kind of cozy. I sort of like it.
And they're like, you know, I mean, like, yes, he doesn't always do the right thing, but like he's under a lot of pressure.
My mom watches a lot of documentaries about this stuff. I'm just like, oh God. No.
My wife likes to watch this show called Snapped. You guys know this show? I don't think she'd want me to tell people that she watches it, but oh my God. Like I walk in and it's like, Greg thought it was just another morning going to work. Little did he know, 3 hours later, he would be dead. And it's like always the wife that does it, apparently.
You should be concerned.
This should be concerning, you know? Like,
Right. I wonder if she's getting pointers. I don't know. It's hard to say. Little did I know she was getting pointers from the television show she was watching. But it always like sounds so dramatic when they're introducing this new thing. I'm like, well, yes, no, clearly I should watch this because something important's going to happen. Everybody turn and look at Shelby.
Hi, Shelby, I do it. Ice cubes. I'm going to try them. They're not ice cubes yet. They're just water.
Okay. Fourier series. Oh man, that was all being recorded on video. Hello, Internet. Fourier series.
Your YouTube channel must be awesome.
It is. And this is going to be a really good lecture, too. Might have to cut this out. I don't usually do editing on this, but this one's just going to be like...
Was that sort of like embedding your video thing on there now, or no?
It's not embedding it right now, it's just recording it. So technically I could stop it and restart it. Meh. That'll be good. You can always fast forward.
Each one of these videos adds like 1,000 subscribers.
Yeah. This is like why people definitely watch my YouTube channel, just for fun. Fourier series are a mathematical series that can represent a periodic signal as a sum of sinusoids at different amplitudes and frequencies. It's like my one-sentence elevator speech for Fourier series. So they represent a periodic signal. Whew. And as a sum of sinusoids of different amplitudes and frequencies. They're useful for solving for the response of a system to periodic inputs. And that's actually why they were developed originally. However, they are probably most important conceptually. They are our gateway to thinking of signals in the frequency domain. That is, as functions of frequency, not time. Okay. To represent a function as a Fourier series is to analyze it as a sum of sinusoids at different frequencies omega n and amplitudes an. Its frequency spectrum is the functional representation of amplitudes an versus frequency omega n. Okay, so we'll begin with the definition of the Fourier series in trigonometric form. There are two forms that we're going to consider, the trigonometric form and the complex form. So we introduced trigonometric first because it's a little bit more intuitive. Okay, so the Fourier analysis of a periodic function, y of t, is for n being a non-negative integer, so 0 and then 1, 2, 3. And period t, we have the an, what we'll call components being these integrals. So you have to do an integral for every one. So that, is good times. But if you do the integral in general for any n, then you don't have to do the integral over and over again. Just do it once for any n. You got to plug in your function, y of t, here. So you take in your function, you're going to write a Fourier analysis of, and you pop it in as y of t, and you do the integration, and you find the an's and the bn's, okay? And the an's and bn's are going to represent the spectrum, and we'll talk about more specifically how later on. The Fourier synthesis of a periodic function y of t with analysis components I did j, but I switched over to n's later, so my apologies. These little j's should be n's. A n, b n to omega n is you sum up these components that you've calculated. So say you calculated these an's and bn's, you can put them in this sum and you can reconstruct your original function in theory. So you got to do an infinite number of them to get back to the original function, which is a lot. But, they don't call it work for nothing, right? So you gotta compute the an's and the bn's, and that gives you this representation. So this is kind of like it's circular, right? You go from a function to the series components, and then you can reconstruct the function from the series components. We don't typically do that. We don't typically do an analysis and then synthesize it, but we're gonna do one or the other. We're gonna either do an analysis on a signal, or we're going to construct to synthesize a signal. Most typically, we will do an analysis and find the spectral components.
But that's why this was created, right? So that if you could have just a few components, you can construct a formula for it, or vice versa. So you can have the option of going back and forth depending on what you need.
Yeah. So it's saying you could either represent it in this form here, where you have these spectral components, an and bn, or you could construct it as a time domain function, y of t. So, yeah.
This is just for periodic, right?
This is just for periodic functions. And later we'll learn another technique that's very analogous called the Fourier transform that will be for aperiodic functions. Yes. Get ready. It's coming. Probably Monday. This is the definition, and typically we're going to start off with some function y of t, and we're going to find all of the an's and the bn's. An, bn, and we're going to do something with it that I haven't defined yet, but we're going to construct a line spectrum with it a lot of times. You could use this to approximate a function. This is not particularly useful, but the example that I used to do for this is that we would construct with the first 5 of these spectral components. So compute A0, A1, A2, A3, A4, A5, and B1 through 5, and then sum them up, and then you can start to see the original function start to emerge.
Oh, that little line thing with the dots at the end of them? Or
Well, and then one of these pages is there's going to be something that's kind of like that. So we'll come back to this. And then you can tell me if that is the case. Okay. So let's consider the complex form of the Fourier series, which is analogous to the trigonometric form. So the Fourier's analysis of a periodic function, y of t, is for non-negative integers and period t. So instead of having 2, you just have 1, but it's complex. So, and there's also there are positive ones and negative ones. So C plus n, and interesting fact that can be deduced from this is that C minus n is equal to Cn complex conjugate. But in any case, if you, oh, I'm missing something in here. What am I missing from this formula? What do you guys think I'm missing? Y of t, right? In the other one, in other components, we had to integrate over y of t times cosine, y of t times sine. We got to interpolate y of t in there. I'll erase that because it's kind of hard to see. But you got to put y of t in there, multiply it by e to the negative j 2 pi nt over t, and do the integration. Notice that we're integrating in all of these over one period, right? So in the bn's and the an's, we integrate over one period. In the cn's, we also integrate over one period. It doesn't actually matter which period you integrate over. You could integrate from negative t over 2 to t over 2, or you can integrate from 0 to t, whatever you prefer. Should be the same result. Okay, so that's the analysis side. For a synthesis of a periodic function y of t with analysis components Cn corresponding to omega n, frequencies omega n, is this. So you sum up all of the components times e to the j 2 pi n t over t, and you get back your original function. So either you can represent it as a sum of sinusoids. I mean, in this case, it's complex exponentials, which using Euler's formula is related to the sinusoids, right? What's Euler's formula?
Oh crap. Is e to the I t e to the I t?
I'm going to use j because we use a lot of current. And okay, e to the jt
Is equal to cosine. It's cosine
t.
Cosine t plus. I can't remember it. It's sine.
Yeah. So that relates these exponentials and these trig functions, right? So that's why we have an exponential here, and it's equivalent to these cosine and sine representations. So you can do it either way. We call the integer n, so notice how this is like there's a component, 0 component, 1 component, 2 component, etc. We call each n a harmonic, and the frequency associated with it, omega n equals 2 pi n over t, the harmonic frequency. So if you come back over here, it's easier to see that a component at, say, like A7, so say you're summing up all these cosines and sines, and you're at A7. A7. And your cosine is then cosine of 2 pi times 7 divided by big T, whatever your period is. 7's not very clear. Times time, right? So this is your frequency, omega n, at any time. And so this is your omega, not just any n, this is your omega 7. So this would be the 7th harmonic, because n equals 7. And the harmonic frequency for n equals 7 is whatever omega 7 is. That's the harmonic frequency. There's a special name for the first harmonic, n equals 1. We call that the fundamental frequency. It is called this because all other frequency components are integer multiples of it, right? So if you were to plug in 1 here, it's going to be 2 pi over t is the fundamental frequency. Then as you increase the number, 2, 3, 4, 5, 6, 7, they're all just multiples of that fundamental frequency. So integer multiples of it. All right. It is also possible to convert between the two representations above. So the Fourier Series converting between forms box gives you that. I don't know what. So there's some weirdness here with the brackets, but the M is not a thing. This is just parentheses.
That might also be in yours.
Oh, it's not showing up on yours that way?
Here we go.
Yeah. Yeah, I think it's when Illustrator imports it, it freaks out on the brackets. Okay, so the complex Fourier analysis of a periodic function y of t is for non-negative integers n and an and bn as defined above. So notice that we use a plus minus symbol in the denominator here, and then we use a minus plus in this one. What it means is that the plus matches up with the minus. Oops. So this one's a minus plus. So the plus matches up with the minus, and the minus matches up with the plus. That's what that means. It's some notational stuff that you might not have seen before. You've probably seen plus minus, but plus minus flipped over minus plus is meant to represent you match the top ones together and you match the bottom ones together. Okay, so this gives us a way to compute the C's from the A's and the B's. And we could just use that to compute the A's and the B's to compute C if we wanted to. And conversely, if you wanted to just compute the C's, you could compute the A's and the B's using these expressions here, 2.16, 2.17. Okay, so that's how to do the Fourier series in complex form, trigonometric form, how to go in between the two. And now we're going to start using them for something specific to construct this spectrum. This is what we really want to get out of this. So the harmonic amplitude, this is sort of a definition, is defined as being the square root of an squared plus bn squared. It's also algebraically equivalent to this. This is missing conjugate in there. Cn and then C minus n conjugate. You could put the conjugate on either one. Same result. So this harmonic amplitude is what we use to construct a line spectrum, which is a graph of the harmonic amplitudes as a function of the harmonic frequencies. The following illustration demonstrates how sinusoidal components sum to represent a square wave. A line spectrum is also shown. So, this is how life works. Actually, so an oscilloscope, well, modern oscilloscopes are just digital, actually. They're just doing a bunch of digital signal processing, and then they represent it on the screen for you. But old school oscilloscopes used to actually have like a physical like electron shooting across the screen, which is cool. I'm going to sidestep the oscilloscope discussion of this, and we'll come back to it at the end. Remind me, we'll talk about oscilloscopes versus spectrum analyzers. Okay?
Only asking because of the shape of the...
Right, it looks like something you would see on an oscilloscope. Totally. Yeah. So let's take a look at this figure, which I borrowed somebody's code to, and then I made it into my own thing. But beautiful figure. And I can only take partial credit for it because I only constructed it. I constructed it with some help from somebody else's code. So pretty sweet though, right? All right. So now that we've just decided it's pretty, let's decide what it means. So we've got in the sort of horizontal plane here, we've got time and we've got frequency, okay? So we're trying to represent a square wave, which let's remind ourselves what a square wave looks like. A square wave looks like, I'll get a different color. So the square wave looks like something constant, dropping down to negative version of that constant, and then back up to something constant, etc., right? So that's the square wave. We want to represent that using a sum of sinusoids at different frequencies. Now, so it's periodic, so that meets the condition. It had to be periodic. And let's draw a graph of what the first, so if we computed the harmonic amplitude, C1, then we would have gotten some value, whatever that is. So you compute the A1, you compute the B1, back over here. So compute the A1, compute the B1, combine them to give us this harmonic amplitude, C1, and we get that. So there's some component, we're going to represent that by a height on the spectral amplitude line. And that corresponds to a sine wave at this fundamental frequency. So this is the fundamental frequency. So I would call this omega 1 fundamental. And notice it has the same frequency as the square wave does, right? So this sine wave at the fundamental frequency corresponds to the frequency of the square wave. And it's got a pretty big component of that. Now we're going to go to the second harmonic, omega 2, so that frequency. And it's going to have twice the frequency of the initial one. In fact, well, this is, I'm going to give away something. I don't want to give away something, but this is another one above it at a higher frequency. And you increase as you go along here. These are all the fundamental frequencies as we go up. Notice that their amplitudes are dropping off. We could compute what those amplitudes are using ANs and BN formulas.
So the red one is not omega 1. It was the first sinusoid.
Correct. The red one is the sum. So the red one is approximately y. But notice that it's only partial sum. Like they only summed up, like for this figure, we were only summing up to get the red, like the first 5 or 6 components. And so it doesn't quite look like a square wave yet, but even after 5 or 6 components, it's starting to, right? And it looks like something like a square wave, but with more wiggles. This is very characteristic of a partial Fourier series that you just sum up some of it. It doesn't quite get rid of all the wiggles. You have to take all of the components to get rid of all the wiggles, which we never actually do. But that's the idea, is that you could sum these up. So like imagine that you went this way and you just started just adding this wave to 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 this wave, you get the red one. Alternatively, you could think of taking this, so that would be a Fourier synthesis. If you went the other way and you started with this square wave and you started breaking it down to all its components, so break it down to this component, this component, this component, this component, that's a Fourier analysis. So notice that like all of that information in the spectral side, we don't really have to draw all the sine waves. The really interesting thing is what frequency it's at and what the amplitude is of that frequency. So we can just get away with drawing this little spectrum, a spectral amplitude, a line spectrum, to represent the frequency domain by itself. Okay. So the example problem is to just compute the spectral components for this problem, for a square wave, the first 5 harmonic amplitudes. And so we'll go through that and do the actual dirty work. But the idea is that we're going to get something that looks like, C1's pretty big, and then they're going to drop off. But let's compute that and find that to be the case. Okay? Now this is where the actual maths start, where we actually have to start buckling down and doing integrals.
Let's go.
But now we're ready because we have more coffee. So, assume that this square wave has amplitude 1. I didn't show it to have whatever amplitude it has. So we'll assume it has amplitude 1. Let's start by computing. I'm going to stick with this green for a while. I kind of like it. Compute a sub n. Is everybody seeing the green okay?
Yeah.
Okay. So I know green color blindness would probably really suck right now. So, all right. The formula is an equals 2 divided by t, integral from minus t over 2 to t over 2 times y, or of y of t cosine 2 pi n t over big T dt. So that's our formula. Let's plug in y of t. So y of t is, of course, the square wave. And we've discussed, you can define a square wave as either having it be an odd or an even function, I guess, because you can either have it the center of one of its hills to be centered at 0, or you could have it be more like a sine where it starts the hilltop at 0 and goes to the right. So we did up here, we said, oh, okay, it's an odd function, right? It's centered like that. But we could have put the axis there, but we didn't. In an arbitrary way, we determined that was the way to go. So, anybody have any idea what to do? We have a piecewise function here over the negative t over 2 to t over 2. So over a period centered around the axis, it's piecewise defined. So how are we going to integrate over that? We could just have 2 intervals, right? Yeah. Integrate over the first interval and integrate over the second interval. Yeah.
Isn't there a trick where you can, if it's odd and it's
you, sir, are head. Shh. No, you're right. You're right. But we're going to discover that. Yeah. You're not supposed to know that yet. But if I had known that you knew that, we could have maybe just skipped this whole lecture.
We don't all know that.
We don't all know that, so we should, yes.
I know nothing.
I probably know, but I don't know that I know. Right?
No, it's true. It's true. We're going to discover it in this example, though. Yeah. So I was just joking with you. I really do want you to speak your mind in class, so as long as I agree with it. Oh yeah, the first interval, let's take the first interval over which the square wave is constant from minus t over 2 to what? 0. And then it has the transition, right? So what is y of t during that interval? -1. We decided that it has amplitude 1, so -1. And then cosine of 2 pi n t over t dt plus 2 over t times the integral from 0 to what? T over 2 of what is y of t during this interval? +1, so that essentially falls out. Stick in cosine of 2 pi n little t over big T dt. All right. So now I'm going to make an argument. Because cosine is even, if we integrate over -t over 2 to 0, or from 0 to t over 2, they're going to have the same value.
Just multiply by 2.
So you could just multiply by 2, but they have opposite signs. So therefore, they're always going to have equal magnitude and opposite sign. And they will, in fact, add to 0. Did everybody follow that? Don't muddy the waters. because
Don't get real world
because cosine is even. That was the argument that I made. Now, this actually can be extrapolated. There's a broader argument to be made here. And that is that if our y of t, so in this case the square wave, but our y of t, if our y of t is odd, an always comes out, all of them always come out to be 0. Okay? If our y of t is even, our bn's always come out to be 0. Okay? It's a nice little handy shortcut for not having to compute a bunch of integrals. But, you know, it's up to you. Sometimes they're just fun. So, that is, our ands are all 0. Now let's compute our bn's. And they're not all 0. Otherwise, it would be real boring. Not very exciting. So, our bn's, let's say, we'll write down our formula, bn.
What does that say about BN?
It said this part?
Compute BN.
Compute bn.
Okay.
It looks like ion, but it says BN.
Compute bn. That made it worse.
Yeah.
Is this more clear?
Yes, actually.
Great.
That's beautiful.
Okay, so bn 2 over t times the integral from minus t over 2 to t over 2 times y of t, same stuff, times sine this time, of 2 pi n t over big T dt. And once again, we're going to break it down into the two halves, right? Because y of t is a constant -1 from negative t over 2 to 0, and a constant positive 1 from 0 to t over 2. And what I'm going to claim is that if you do those maths, you will get 2 divided by n pi 1 minus cosine of n pi. Which can be sort of piecewise defined a little bit simpler as being 0 whenever n is even, and as being 4 over n pi whenever n is odd. So pretty nice kind of in the end. Especially painless when we skipped from this line to this line. That was nice. So all that's left is to just plug into that simple formula what our harmonic amplitudes are. Therefore, remember that our harmonic amplitude formula states that Cn is an squared plus bn squared, right? Square root of an squared plus bn squared. So, an we have conveniently computed to always be 0. So that term's gone. So it's essentially the absolute value of bn that we're left with for each case. So C0 is an is always 0. B0 is, so 0 is an even or an odd number? Even. It's even. I know.
Oh, yeah.
Wikipedia says it's even.
I would argue that 0 is not a number because it's the last.
The problem is if n is 0, plug that into.
I'm not gonna go on that. We're already over time, so I'm just gonna compute. But I'm gonna say that 0 is even, and if you don't know for sure, you always come back here, plug cosine of 0 in, which is 1. 1 minus 1 is 0. Bn, or b0, is definitely 0. And square root of 0 squared plus 0 squared is definitely 0. C1 is going to be 4 over 1 times pi, which is just pi. C2 is 2 is even, so that's going to be A2 is 0, B2 is 0, so C2 is 0. And C3 is going to be 4 over what? 3 pi.
I have a feeling that, like, if you draw this out into infinity, there's some sort of, like, series.
And then finally, yeah. So these are our components that, there was a bit of a swindle here because you're seeing only every other. So you're seeing C1, this is actually C3, and this is actually C5, etc. And so really this is omega 1 and omega 3 over here. Yeah.
Do you intentionally avoid C4?
Sorry, say that again?
Do you intentionally avoid C4?
Yeah, it's explosive. Yeah. So that is how to do. So notice how we already can think in terms of this frequency spectrum. We're thinking in terms of the frequency domain for this function. It's got strong frequency components at these multiples of the fundamental frequency. Okay, and that's sort of the introduction to Fourier series, and you guys will get some practice in the homework on Fourier series. Yeah.
Are we assuming the period's 1?
We actually never assumed that the period was anything.
It just comes out?
The period fell out.
Okay.
So yeah, we never assumed it was anything. So this works for any period of a square wave. I did assume that the amplitude, I could have just left the amplitude as A,
Yeah,
and then you can end up with an A in these expressions. Yeah. But I assumed it was 1. There's less writing.
There's a quiz online right now. That's
There's a
based
quiz
on
online
that we just did.
soon.
Oh, not yet.
That
Like message us in some way. when
yeah,
you
I'll do it. I'm just gonna go to my office and finish it. So
Okay,
within
are
the
you
next
going
half hour,
to
it should be.
increase the time in which it is due?
Yeah, I might make it due tomorrow. I'll make it due tomorrow noon, so that you guys have a little extra time, because it's not up yet.
But you are gonna put it up today.
I'll put it up. Yeah, as soon. I mean, I'm gonna go back to my office and.
I mean, because
Put
if
it up.
not, I was prepared to sit at my computer and refresh it every 10 seconds